Hello and welcome back, my pre-calc peeps. Today we are kind of starting to put everything together that we've learned in chapter 7. So solving basic trig equations is what we're going to be tackling today. Again, these are just basic trig equations where you can start to make some connections. Everything starts to come together. And it's pretty neato. With me, of course, your host, Miss Passmore. And today we're just going to be able to solve basic trig equations for roots in the interval 0 to 2 pi, and also for all real roots. And you'll see what I mean by then. So accounting for all of them forever and ever. A lot of times we had like plus 2k pi, things like that. So our unit circle is going to come back and haunt us. So I got a little colorful one popped up right here for us. I shouldn't say haunt. I love the unit circle. That's my jam. And we're going to be exercising our brain and going back to kind of some really basic problem solving strategies. That doesn't even necessarily have to do with trig. So I don't think you guys are going to hate this. It's not going to be like your proofs that you hate so very much. And today we're just going to do like 5 problems, just straight up off the bat. I totally have confidence that you guys are going to be able to handle this like nobody's business. So let's just get into it, shall we? All right, so our very first basic example says to find the principal root of radical 3 tangent x minus 1 is equal to 0. And the principal root just means that it is the root associated with our reference angle. So just I wouldn't get too caught up on the wording of if it says root or principal root. It's like the main guy that we would use to determine any other potential roots in 0 to 2 pi. So here is our equation. We've got radical 3 tangent x minus 1 equals 0. Now we've been doing a lot of stuff with the verifying identities, but we haven't done anything with like solving. So remember that when we are solving something, we are looking for intersection points. So we're going to do exactly that with this equation. We're going to find out when does this tangent function intersect a particular function. So let's just start off basic, right? Like we're going to start this like we normally would. If this wasn't tangent of x and it was just like radical 3x minus 1 equals 0, we would start this the same exact way. We're going to start by taking inverse operations until we isolate what we want to solve for. So in this case, we want to solve for our trig function for a very specific value of x. So here's our original equation, right? Radical 3 tangent of x minus 1 equals 0. And if we start doing our inverse operations, the very first thing we would do is add 1 to both sides. So doing that leaves us with radical 3 tangent of x is equal to 1. I almost have tangent completely by itself. The inverse operation of radical 3 times tangent of x would be to divide by radical 3 on both sides. Now I know what you're thinking. You're like, what? Divide by radical? I thought we were not allowed to do that. Yeah. In this particular section, we're not going to be rationalizing the denominators, and you'll see in a second. So if I divide both sides by radical 3, I get tangent of x equals 1 over the square root of 3. Now I know this looks ugly. We're not used to having radicals in the denominator, but trust me, it's okay for this section. Usually you guys tend to want to skip that anyway. Or you could say, when is tangent of x equal to radical 3 over 3, if it's really, really, really bothering you. But what I mean when I say that whenever we're solving something, we are solving for intersection points. I want to know when the tangent function has a height that's equal to 1 over radical 3, or radical 3 divided by 3. And that's what I'm looking for. So in this section, and the previous section actually that I kind of glazed over and skipped and had you watch a really good video about, they really, really emphasize graphical information as well. So really making the connection between what you're doing and what you're getting, and does that make sense? That's what we're doing, because we do refer back to our images a lot, refer back to our pictures. But I want to know where the intersection point of these two separate functions are. So this is the tangent function, and then this is a constant function. Where do they equal each other? Where do they intersect? Now, I can't just divide by tangent. That makes, one, no sense at all. But I still want to use inverse operations, so I can actually take the inverse tangent of both sides, because I want to solve, whenever we're solving 2, we solve for a very specific value of x. I want x equals something. I'm not satisfied until I have a very specific x value, because it's representing those intersection points. So if I'm not going to tell you exactly where they intersect, what was the point of doing all of this work? Right? And I mean, this isn't a lot of work, but sometimes they can be a lot of work. So we need to find the exact value of x. Whenever we're solving, have an equal sign anywhere, I want a very specific value of x. So I'm going to take the inverse tangent of both sides. And when I take the inverse tangent of both sides, what's going to happen is that inverse tangent cancels out with tangent, leaving behind just x, which is exactly what I want. I want a very specific value of x that gives me where my intersection point is. Now, from your warm-up video, you guys should know what this means, okay? So this is saying that x is going to be equal to the inverse tangent of 1 over radical 3. What that's really asking, there's our nice unit circle coming back, is for what angle theta gives the result of 1 over 3 with the regular function tangent. Like, where is tangent equal to 1 over radical 3? Where is just tangent equal to 1 over radical 3? Because remember, x is a very specific place, and since I'm using inverse tangent, I'm looking for the angle, not the height anymore. So I want to know what angle gives me 1 over radical 3 for tangent. So this is really, really important. What angle gives 1 over radical 3 for tangent? And then also from the warm-up video, remember that for tangent, we have a restricted domain from negative pi over 2 to pi over 2. So let me grab a highlighter here really quick. And negative pi over 2 to pi over 2, okay, remember this is 0 degrees, and this way it goes 0, 90, 180, 270, 360, right? Pi over 2 is 90 degrees, and negative pi over 2 is just 90 degrees in the opposite direction. So my domain restriction, oops, it's a little janky. I'm using my mouse. Is this area of the unit circle. I can only do this like quadrant 4 and quadrant 1, right? Negative pi over 2 is just 90 degrees in the negative direction. Pi over 2 is 90 degrees in the positive direction. It's bugging me that it didn't write so nicely. Whatever. Okay, so looking at this, what tangent is sine over cosine? Where am I going to get 1 over radical 3? That is going to be right over here at pi over 6. Notice that this is cosine comma sine, so I'm going to have 1/2. Realistically, I'm going to have 1/2 divided by rad 3 over 2. Keep, change, flip it. You have 2 multiplied by rad 3. That definitely gives you 1 over radical 3. And that falls within my domain. So yeah, it's totally going to be pi over 6. So x is a very specific value. You're telling me that the intersection point is at pi over 6, where tangent of x is equal to 1 over radical, 1 over radical 3. And if I took a calculator, I'm saying that it's equal to that specific height. I don't know what 1 over radical 3 is. I should have determined that beforehand, but I didn't. But the goal was to find out a very specific value of x, and we did. We referred back to our unit circle. We answered the question of like how to use inverse tangent to tell me what I'm looking for, and then referred back to what we know, which is really neat and really cool that things are starting to come, pun intended, full circle, full unit circle. And I don't think that was too far of a stretch. Like, you guys are great problem solvers. I don't think that's going to be an issue. So let's try another one. Okay, so for 2 cosine theta plus radical 2 is equal to 0, find all of the solutions in the interval 0 to 2 pi. So as we move on through each example, the equations are going to get progressively more difficult. But I think still you guys will realize, or I hope you realize, how much problem solving capabilities you have here. So again, we're going to start just as we would, trying to isolate our trig function. And then we're going to use the inverse trig function to get just theta alone in this instance. So here's our original equation. We have got 2 cosine theta plus radical 2 is equal to 0. If I were going to isolate everything, I would subtract radical 2 on both sides. This leaves me 2 cosine theta equals negative radical 2. Again, the next inverse operation would be to divide by 2. This gives me cosine of theta is negative radical 2 over 2. And in order to isolate, again, isolate my trig function, I'm here. I have isolated it, but I also need to find a specific value of theta. So I'm going to take my inverse cosine function of both sides. The only way I can get theta alone is if I use an inverse trig function to get rid of the trig function. You know what I mean? So inverse cosine times cosine theta is equal to inverse cosine of negative radical 2 over 2. Remember, whatever we do to the left-hand side, we absolutely have to do to the right. Those two guys cancel out, leaving us with just theta is equal to inverse cosine of negative radical 2 over 2. At this point, when you get to this part in the solving, you're going to want to bring back an image of your unit circle. I want to think back to that, or a lot of you guys have this ingrained in your memory because we referenced it so much at the beginning of the year. But again, we're going to ask ourselves, what angle gives me the output of negative rad 2 over 2 for cosine? Right? I have inverse cosine over here, but I want to know what angle, what specific angle gives me negative rad 2 over 2 for cosine. Again, since I'm dealing with cosine and inverse cosine, I have a restricted domain. So my restricted domain is 0 to pi, okay? 0 degrees to pi degrees, 0 to 180. So I can only work in quadrants 1 and 2 for this. So I'm looking, where can I find cosine? First of all, cosine. Remember, it goes cosine sine, negative rad 2 over 2. Here's rad 2 over 2, but it's not negative. Boom, right there. Yep. And the specific theta value, my specific angle, is 3 pi over 4, or if you like using degrees, you could say that's 135 degrees as well. That totally works, but we can clearly see that x is equal to 3 pi over 4. That should actually say theta, whatever. You gave us a very specific value for theta of where this is going to be true, where cosine, we're really finding out where cosine function is equal to negative rad 2 over 2, where cosine has a height of negative rad 2 over 2. So remember how I was saying that the book and I personally value knowing what this looks like conceptually, right? We were finding intersection points, and we found a very specific value, and it looked a little complex, but it wasn't that bad. So here's the graph, okay? Let me erase these, that domain right there, okay? So we can see clearly that we've got cosine being our black function, right? Starts at 1 and continues on. It has a period of 2 pi. So it starts at 1 and it finishes its cycle at 2 pi, right? And then negative rad 2 over 2 is just a constant line down here. Negative rad 2 over 2 is a little bit less than negative 1, okay? And I'm saying that in the interval from 0 to 2 pi, my graph intersects right here and right here. Now, I know it looks like there's two intersection points, but what happened is actually one of them is extraneous. So one of them isn't falling within our domain restriction. So because we're talking about cosine and inverse cosine, we have to restrict the domain from 0 to pi. So I'm saying only in this chunk is where I'm looking for a solution. Therefore, I only have this guy. Right? Because if I was looking for where I'm going to get negative rad 2 over 2 for cosine, if I go back to my unit circle, I'm also going to get negative rad 2 over 2 for cosine right here at 5 pi over 4. But I said that our domain was restricted from 0 to pi. So that's why I only included just the one. But from this image, you see both of them, which is pretty neat. So we have to think about our domain restrictions from the warm-up video. Let's do another one. Like I said, these aren't too crazy terrible. Okay, elevated a little bit. Example 3. For tangent squared x minus 1 is equal to 0, find all solutions in the interval from 0 to 2 pi. So this one, we are going to still take our inverse operations until we isolate our trig function, or just a thought, you could try factoring. We're not going to try factoring here, I don't think, on this example. But in the future, whenever you're solving, again, when we're solving, we're looking for intersection points. We can use any algebraic strategy that we have that works in algebra. It works in trig too. We just have to think about where is my function living or where is it not living at this point in time. So let's start off. We've got tangent squared x minus 1 equals 0. Now, this one doesn't have as many terms in the original equation, but it does have a tangent squared, which is a little tricky. Again, inverse operations are just going to tell us to add 1 to both sides. So if we add 1 to both sides, we get tangent squared of x is equal to 1. And remember, tangent squared, right? Tangent squared of x really means tangent times tangent. Tangent x times tangent of x. I really wish I wasn't using a mouse for this, but whatever. Tangent squared x is tangent x times tangent x. So the only way I can undo that, I'm trying to use inverse operations. Inverse operations undo algebra. And I'm going to have to take the square root of both sides. If I take the square root of tangent squared x, if I take the square root of these two guys over here, oops, see, if I took the square root of two things multiplied, I'm just left with tangent. And the square root of 1 is, well, plus or minus 1. So here's something that's a little different than the last problems. Now I have two options. I have plus tangent of x could equal positive 1, and tangent of x could equal negative 1. I have two separate situations that I need to take the inverse tangent of. So I kind of split this into one equation over here and another equation over here. I have tangent of x equals the positive 1 option, and tangent of x is equal to negative 1. Again, I finally isolated my trig function. Now I'm going to take the inverse tangent of both sides so that I am ending up with just x, inverse tangent and tangent. So I end up with x equals inverse tangent of 1, or x is equal to inverse tangent of negative 1. Looking back at our unit circle, I'm really asking myself, what angle measure gives me the output of 1 when I have tangent, or negative 1 when I have tangent? So again, this question comes up all the time, and I keep writing it out for you guys. What angle theta gives the result of positive 1 or negative 1 when we are using the tangent function? So remember, tangent is sine over cosine. Which one is going to give us 1 or negative 1 when we have tangent? And again, our domain is restricted. So for tangent, we are restricted from negative pi over 2 to pi over 2, which is negative 90 degrees, or all the way to positive 90 degrees, or negative, or 270 to excuse me, 270 degrees to 90 degrees. Okay, so I want to know, when is tangent going to be positive 1 or negative 1? Remember, tangent is sine over cosine. Clearly, that's going to be here or here. Let's see. Yes, of course, because rad 2 over 2 divided by rad 2 over 2 is 1, positive 1. And also, negative rad 2 over 2 divided by rad 2 over 2 is going to be negative 1, right? So we get pi over 4, and then this is technically negative pi over 4, but I actually don't like calling it negative pi over 4 because I'm of my domain restriction. So let's just rename it to 7 pi over 4, okay? Because we're dealing with, when I say this, because, well, here's a better explanation, is pi over 4 is this initial angle. And of course, you guys can see that it's 7 pi over 4 too, because I have this. But this, pi over 4, this is my reference angle in quadrant 1. So because of symmetry, I know that I'm also going to have this reference angle, and that's going to be negative theta, or negative pi over 4. So that's where I'm getting that value. Obviously, we know that negative pi over 4 is 7 pi over 4, so I don't want to use this notation. I would much rather use just pi over 4 and 7 pi over 4, because the problem asks us for all solutions in the interval of 0 to 2 pi. Negative pi over 4 doesn't fall in that interval. I want 0 positive angle measures, not negative angle measures. So we would just change that and replace it with those two values. And then also, because I'm asking from 0 to 2 pi, I'm also going to include all of the other times where I could get positive or negative 1. So initially, my domain was restricted here. That's where I figure out, well, what angle measure is going to do it. This is my reference angle again, but again, because of symmetry, that connects all the way over to this angle. Because of symmetry, that connects all the way down to this angle, and lastly goes back over to this angle. So all four of those angles actually are what I'm looking for, because I said to find all of the solutions in in a particular interval that's given. Now, if I didn't make this stipulation, if I just said for tangent squared of x minus 1 is equal to 0, solve, then I would just have pi over 4 and 7 pi over 4. But since I said in 0 to 2 pi, every single one where we're going to get an output of positive 1 or negative 1 for tangent, I need to include all of them. I hope that makes sense. It's because of this interval right here that kind of changed the game. And that's something that's new in comparison to what we had talked about for the previous two examples. I love symmetry. It's so nice. Okay, we only got 2 more problems, so let's amp it up a wee bit here. Oh yes. So again, because, let me get rid of all of this writing. Because we were talking about really emphasizing the importance of visually representing things. So tangent of x is represented as the black graph, right? And then when we were solving the equation, we were saying, well, where does tangent equal plus or minus 1? This is what we were really asking. Where's the intersection points? So we can see with y is equal to positive 1 and y is equal to negative 1, I have 1, 2, 3, 4 intersection points. These all fall from 0 to positive 2 pi, which is where all of those points are, right? So this is our pi over 4 value. This is 3 pi over 4, 5 pi over 4, and 7 pi over 4. All of those 4 points fall within the interval from 0 to 2 pi, which is why I have to include all of them. And they are relating to having a height, like the tangent function has a height of positive 1 at pi over 4 and 5 pi over 4, and the tangent function has a height of negative 1 at 3 pi over 4 and 7 pi over 4, because that's exactly what we're asking right here. This tells us that we're looking for intersection points. So hopefully it's all kind of coming together. Okay, let's amp it up just a tad. I do think I love this problem just because I love the strategy that we're going to use so much. And if you're going into calculus, this strategy is honestly one of the best. It was one of my favorite strategies too. So for 3 times cosine squared theta plus cosine theta minus 2 is equal to 0. Find all solutions in 0 to 360-degree intervals. So this one we're changing to degrees instead of radians, which is fine, no big deal. You guys probably like degrees anyway. So if you have a calculator out, make sure you have your calculator in degree mode. And we are going to, again, find all of the solutions here. So this one has a lot more going on, but never fear. We are going to start off by simplifying the equation. So we're going to use a U substitution, and this is why I said this is my favorite, because it's one of my favorite strategies. So U substitution just simply just makes the equation something simple that we know how to work with, that's not overwhelming to look at. We know how to solve that problem, and then we go back and resubstitute in what how we made it so simple in the first place. So the reason we're going to use U substitution is because I noticed looking at this equation that I have cosine written multiple times. So I can, make cosine an x or a u, or since we're doing U substitution, we let it be called u. So that it becomes an easier problem. Now, the reason that we don't call it x is because you could get confused, because we're going to end up solving for a specific value, and that specific value is typically x. Here, the variable we're using is theta, but nonetheless, we don't want to get confused. So typically we use U substitutions when we're trying to make things simple. I love this strategy. So we're going to simplify it, and we're going to end up with a quadratic. Then we're going to factor. Okay, so we're going to let U equal cosine of theta. So everywhere I see a cosine, we're going to substitute in u. Now, whenever you do a u substitution, I'm telling you right now, you need to write down on your paper for yourself and for your teacher what u is equal to. You must write down this statement, let u equal cosine of theta. Otherwise, you're going to forget, you're going to think you solved the problem, and you missed a lot of things. So let u equals cosine theta. Now I'm just going to write down the equation again. 3 cosine squared theta plus cosine theta minus 2 is equal to 0. We're solving this. And wherever I see a cosine, I'm going to substitute in a u. So this is going to become 3u squared plus u minus 2 equals 0. Do you see where those cosines now became my u's? Okay, this is easy to work with. You can totally factor this. Remember, when I have a quadratic equal to 0, that means I want to find the roots. And the ways I can find the roots is through factoring, through the quadratic formula, and if they are like a special instance, I could complete the square if I really wanted to. But usually factoring and using the quadratic formula are fail-proof. So this is actually factorable, so it's going to be 3u minus 2 times u plus 1 is equal to 0. And again, when we have quadratics equal to 0, we're finding the factor. Set each factor equal to 0, and we get u equals 2/3, and u is equal to -1 by setting each piece equal to 0. Using that zero product property, if something times something equals 0, either the first something is equal to 0, or the second something is equal to 0. Okay, so this is what I mean. If you didn't say u is equal to cosine x, you would think we're done and we got two specific values that it works with. But I didn't really have just u to work with at the begin with. I didn't really have something this beautiful and simple to begin with. I had my function in terms of cosine. So I really have to say u, if u is equal to 2/3, since I let u equal cosine of theta is equal to 2/3, and also cosine is equal to -1. You've got to convert back. So you start by making it simple, and then you have to convert back. If you don't convert back, you didn't solve the problem. You found most of it, but you didn't solve the problem. So pro tip, if you use u substitution, you have to back substitute it in as well. Okay, but then this isn't so bad though, because this is basically where the last three problems were at. In order to get theta alone, I just have to take the inverse cosine of both sides. Right? Inverse cosine of theta is equal to the inverse cosine of 2/3. Boom, boom, I'm left with theta. And then the second half is going to be inverse cosine of theta is equal to inverse cosine of -1. So I really have two options. Theta is equal to inverse cosine of 2/3, and theta is equal to inverse cosine of 1. Now I'm back at, where we have been for the other problems. Here's our unit circle, and we're going to beg the question again, for what angle do I get the output of 2/3 and -1 for cosine? What angle gives the result of 2/3, 2/3, or -1 for cosine? Remember, cosine is the first coordinate, cosine comma sine. So I don't have 2/3. Cosine, I don't see any 2/3 here. But I do have -1, and we have a restricted domain from 0 to pi. But we're also finding all of the solutions. So let me draw my restricted domain really quick. 0 to pi, so this is 0 degrees. We're at pi over 2 and pi, so we're looking for where is this going to happen? Well, we're also in degrees. So I don't see 2/3 on my unit circle because it's kind of weird, right? But I do know cosine is going to equal 1 at 180 degrees. -1 at 180 degrees right there, in a really sloppy way, right? So for this problem, you can actually use your calculator at this point. You can use a calculator. Whoa, Calc. You can use a calculator to help us figure that out. But 48.2 degrees is a little bit past 45. So that's going to be like somewhere right around here. Just kind of drew that guy. And that is within my domain, right? That's within my domain. This is going to be one of my, ooh, that is so janky. That is going to be one of my reference angles that I'm going to use because again, although I have a restricted domain, it wants all the solutions from 0 to 360 degrees. So here, pretend this is straight, is one triangle with my angle theta of 48.2 degrees and also 180. Now notice this angle is a quadrantal point, so it is not going to have a difference reference angle from it, but this guy is. So the normal things that we get from our calculations are 48.2 degrees and 180. Yeah, that's what we're going to get. But that's just within my restricted domain. My actual problem asks for all of the solutions, absolutely every single one, in 0 to 360 degrees, including 0 and up to 360. So since the problem says from 0 to 360, this one doesn't have a reference angle, but this guy is in quadrant 1. Because of symmetry, I could draw this guy way down here, and he's going to be somewhere down there. I just kind of drew it haphazardly. It happened to end up nicely, but because this is my reference angle, because it's in quadrant 1, that's my reference angle, I know that this value right here is also going to give me an output of 2/3. That is also going to give me a height of 2/3. So I have 1, 2, 3 values where my function is intersecting. I have 3 intersection points where I get those specific outputs. So 48.2 degrees is this first guy over here in quadrant 1. 180 degrees is right on the border between quadrant 2 and quadrant 3. And 311.8 degrees is the angle in quadrant 4. And the way that I got that was 360 degrees minus 48.2, because this is the 360-degree value, and you just subtract off in the negative direction how much your reference angle is. So remember back when we were talking about reference angles, you find the point closest to it. So it's usually 180 degrees or 360 degrees or 270, and you add or subtract whatever your reference angle is. That's what we're doing. Voila. Give you guys a second to process that. And of course, again, we came up with three intersection points, right? When we're talking about that. And we can see here that we have, in fact, 3 intersection points. We've got cosine, and we've got the 2 constant values that it's equal to. Remember, right here, we found out this is what we're checking the intersection points for. Whereas cosine equal to 2 over 2/3, and whereas cosine equal to -1. So cosine equals to -1, that's at 180 degrees. You could see 180 degrees right there. Perfect. And then the 2 other options where it's hitting, intersecting at 2/3 is in quadrant 1 at 48.2 degrees, that really weird angle measure. And then additionally in quadrant 4 at 311.8 degrees. So we can see and verify that these angles make sense. That does actually fall within the interval that I'm talking about. And I found it mathematically by making sense of what I know and what I have in front of me. So cool. I love it. Yeah. Okay, one last problem. And this one is a little different. No, it's not a little different. It's a lot of different. So find all real solutions for cosine of 2x plus sine squared x minus 3 cosine of x is equal to 1. So first of all, This equation is crowded, y'all. It's crowded. It's also very complex looking in comparison to all of the others. And it asks for all real solutions. So this is what I'm meaning, like forever. I didn't stop you on a certain interval from 0 to 2 pi. I want to know forever and ever and ever, what are all the possible solutions to this equation? So this is kind of the very last of the quote unquote basic trig functions to solve. And the last ones we relied on our previous knowledge of algebra, really to work through those problems, and then started to connect the information that we had with what we know about the trig functions and about the unit circle and where they live, right? So now we're going to start to combine another thing that we learned in chapter 7, which was those identities. Yes. Because I have cosine of 2x. First of all, I've got cosines and sines. That's a pain in the butt. I want to have either just one function altogether, or you do something. So I do have a identity for cosine of 2x. I have a double angle identity. This is a double angle. So I can use that to hopefully simplify my equation. So check it out. At first glance, this seems impossible. Like some of you probably would have given up and been like, oh, heck no, you are crazy. We are not doing that. You're absolutely out your mind. But like I said, we've been building up our toolkit. We have so many things that we can use to solve equations, and that's why trig is so fantastic. We really just have so much at our disposal to use. It's just we have to figure out, what do we use? So we're going to eliminate a function by using a double angle identity. Okay, so in case you forgot or your paper's not in front of you, remember that cosine of 2x is equal to cosine squared x minus sine squared x. That is the double angle identity. So we're going to substitute that to where we see cosine of 2x. So here's our original equation. Here's our OG. And we're going to substitute in our double angle identity, just a brief substitution. Cosine squared x minus sine squared x plus sine squared x minus 3 cosine of x. And from here, it's kind of cool because literally this helped me. I said it was going to help us eliminate a function, sine specifically. I even told you, but check it out. I got rid of sine squared x plus sine squared x. Those cancel out and give me 0 sine x. So now I am just left with cosine squared x minus 3 cosine of x is equal to 1. This is cool because now I have an equation only in terms of cosine. I can handle that. I can do things in just sine or just cosine or just tangent or whatever. Throw me anything. If it's all in the same terms, I can probably finagle something. But once it's in a bunch of terms, that's where it really starts to give us some issues. So again, we're kind of going to go back to the strategy that I love so much from the last example and do a u substitution. So, what we're going to do here is subtract 1 on both sides, because now I have cosine and cosine, right? So if I subtract 1 on both sides, I have cosine, and I can do another u sub because I've got cosine, cosine. This is quadratic, okay? So let's let u equal cosine of x. Substituting in my u value, I get u squared minus 3u minus 1 equals 0, which, okay, this looks simple, but the factors of 1 are just 1 and 1. They're never going to add up to being 3. This is not factorable. So although this is nice and simple and makes you happy inside, it's not factorable. We're going to have to use the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Is the quadratic formula. So you have to substitute in those values. So if I did, we would get u equals This should be -3 on the outside. The song goes x equals -b plus or minus the square root of b squared minus 4ac over 2a. When I taught Algebra 1, I played that song far too long. Now it's never going to leave my head. So we plug in this these values, right? We simplify it. We get u equals -3 plus or minus rad 13 over 2. This should be a negative. I don't know what's wrong with me. Should be negative. Oh, minus. No, it's positive. X equals -b, because b is negative to begin with. -3. JK, LOL. Okay, so we get u equals 3 plus or minus rad 13 over 2. I've got two options again, but again, I didn't start with u. I started with things in terms of cosine. So before I go back to cosine, let me get a actual decimal approximation, because I know you guys are all about your decimal approximations, okay? I'm about leaving things the real way they're supposed to be. But I think it's going to be a little bit hard to make sense of the real solutions with the radical, because we're just not good at understanding, like, what exactly is the square root of 13? And if I add 3 to it and subtract that number from 3, where am I? And then, oh, I've got to divide everything by 2. It's just a lot. So let's just convert to a radical. To 4 decimal places. So we're going to get 3.3028 and -0.3028 as our options. Again, this is in terms of u, but we did not start in u. We started in cosine. So cosine equals 3.3028 and cosine equals -0.3028. Again, I don't want a cosine value. I want a specific value of x, because I am solving an equation. So taking the inverse cosine of both sides, I did not show this step. I just canceled it out. X equals inverse cosine of 3.3028 and x equals inverse cosine of -0.3028. Okay. Now, if you plug this into your calculator, you are going to need a calculator. Plugging this guy into your calculator tells you no solution. Error, DNE. That one has no solution. But if you plug this guy in your calculator, it will say 1.8784. Now, make sure, again, you're in radians. So that's going to be 1.87 radians. 1.8 radians, whatever, however you want to justify that. So the first one has nothing. It's no solution. Didn't give me diddly squat. But the second one gave me 1.87 radians. So when I'm figuring out where the intersection points are, and this is in terms of cosine, again, I want to think about my function. Or, I'm sorry, my unit circle. And I want to know what specific x value it is, but we found it. I don't need to find theta. It gave me an exact value actually on this guy, which is really nice. So I have 1.8784 radians, and you're probably thinking like, well, okay, where is that on the unit circle? Now, way back when we decided that pi was 180 degrees, we made an assumption, okay? Pi is 180 if 2 pi is 360, right? Now, pi is 3.14, right? It's also 3.14 radians. So pi is about 3 radians. That's how I always think about it. And because I know, wow, that's supposed to say rad, about 3 rad, I'm just going to erase it because it looks absolutely terrible. But pi is about 3 radian, and if pi is about 3 radian, then I know the entire unit circle is a little bit more than 6 radians, which is actually accurate. And I brought that up. I don't know if you guys remember. You probably don't. But when we first started talking about the unit circle and how many radians go around the unit circle, regardless of the diameter or the radius length. It's always going to be a little over 6. I think it's like 6.2 something. Like that. So if I were to estimate where 1.87 radians is, if this is about 3, this is about 1.5, so it's got to be in quadrant 2, and it's just like somewhere around there-ish, because I'm kind of thinking about thirds, right? If this is a third, and then this is, a third, and then we have that other third leading up to the 1, 2, 3 radians, so it's going to be somewhere over there. So it's ish around there. Okay. But because of symmetry, it's also going to be right down here as well. That's also going to have that same height, because notice in quadrant 2, we have the height is 1.87. So I totally lost my train of thought. I had a brain fart. I apologize, and I can't get it back. So the values, all of the real values were cosine, where they're like factorable, like these values right here, the intersection points is 1.8784 radians is going to be these two specific values. You get 1.8784. Now to find this value over here, we're going to have to take our reference angle and subtract it from 2 pi. So 2 pi, right? This is my reference angle right here. It's in quadrant 2, but my angle here is 1.87. And because of symmetry, it's also going to be in quadrant 3. So the only way to find out how many radians that is to take 2 pi radians and subtract off in the negative direction, 1.87, and that gives me 4.04 radians. So we have two solutions, these two values where they have the same height, where they have the same output value, x is equal to specific radian value, and I get out a specific value. And if I were to combine and get all of the real functions, it would be 1.8784 plus 2 pi k as I continue to go around and around and around. And similarly, 4.4028 plus 2k pi as I continue to circle around and around and around the circle, which is pretty neat. Okie dokie, that's it for today. You don't have any homework. I know, I'm feeling so generous. It's because I don't want to grade your homework. So I hope you enjoyed and have a wonderful rest of your day. Toodaloo. Bye.